Here is the strand shoe we saw in the animated drawing. Now, the spinning carriage comes into the anchorage. The wire loops it has carried all the way across from the opposite anchorage are taken off the wheels and looped around the strand shoe. Then, 2 more loops of wire are placed on the carriage. Off it goes for the return trip, moving up the side span to the tower top. As the wires pass over the tower top, they are placed in temporary saddles until a group of 452 wires form a single strand of the great cable. Let's go back to the building of the George Washington Bridge at New York and notice the great improvement 6 years has wrought in spinning technique. There, only 1 wire loop was carried on each trip. On the Golden Gate Bridge, this rate had been doubled, but Roebling engineers were not satisfied with twice the capacity. They wanted 6 times as much, and they achieved it on the Golden Gate Bridge with 2 developments never tried before in suspension bridge history. As soon as the bridgemen had become familiar with handling 2 loops of wire, the rate of spinning was then accelerated 50% by the introduction of a new type of spinning carriage, which now carried 3 loops on each trip. Secondly, the wires were transferred at midspan. Thus, no spinning carriage had to travel more than halfway across, and the wire spinning capacity was doubled. These 2 Roebling developments have made it possible to open this bridge to the public in record time. At midspan, the wires were quickly transferred, and the carriages are now off on the return trip with a new set of wires. At the tower top, the bridgemen reach for the wire and place it loosely in specially designed clamps or vices. A little way down on the walk, a bridgeman attaches a hauling clamp or come-along to the wire. And 2,100 feet away at midspan, the wire adjuster operates the come-along by means of a push-button control. He raises each wire until it is clear of all obstruction, then lowers it to its position in the partially completed strand. When the adjuster is satisfied that the wire is in its proper place, he gives a signal to the tower top, and the bridgemen tighten the clamps on the wire. When the wire from one reel is exhausted, the spinning carriage must stop long enough to replace the reel with a fresh one. The splice is identical with that made in the reeling plant. To control and guide the many spinning operations, a system of telephone and push-button lights connects many points along the line with the dispatcher's office in the middle of the bridge. Practically all sizes and types of electric cable required were selected from the large Roebling stock. Let's listen in as the main span dispatcher hears from the North Tower top spinning boss late one afternoon in May.
If South Anchorage promised you 2 more trips by quitting time, we'll top it, but clear 'em fast.
And the dispatcher did clear 'em fast, for more than 1,000 miles were spun by quitting time. 1,000 miles in 8 working hours, a record for all time recorded on this Celsin dial. Spinning conditions were not always as calm as we have seen. In fact, when gales blew in from the full reaches of the Pacific, they were worse than any Roebling engineers had ever encountered in their long experience of bridge building. But the bridgemen were never the first to quit. When the needle in this anemometer showed wind velocities over 40 or 45 miles per hour, the bridgemen seemed to delight in fighting the gales. Older and wiser heads among the engineers had to call them down off the footbridges. And despite the many gales, the Golden Gate main cables are rapidly spun. As spinning crews compete with each other, as sharp eyes follow the course of the spinning carriages, and men and machines hurry to the task. Brooklyn Bridge, which amazed your grandfather in his youth, could fit in its entirety, anchorages and all, right under the main span of the Golden Gate Bridge. The next step is to place the suspenders over these castings. The suspenders arrive at the bridge, having been cut to exact length and socketed at the Roebling mills. After hoisting the reels to the tower top, they are trolleyed up to their position, as were the cable bands. Over sheaves which are set on the cable band, they are slowly allowed to drop until the loop is guided into its supporting groove or saddle. Special clamps hold the ropes together below the cable. As we view these suspender ropes which will carry the load of the roadway and its traffic, we may not realize how much one branch of engineering is dependent upon another. Consider, for instance, that not more than 4 of these suspenders have the same length, varying from 23 feet at midspan to 489 feet at the tower tops. Cut to length 3,000 miles from their final resting place, each and every suspender end or socket must come to rest at exactly the correct position. Moreover, it must stay that way through generations of exacting service. Rain, fog, roaring nor'westers, and the pounding of heavy holiday traffic loads. And it will stay that way because so many industries and years have contributed to the science of wire rope manufacture. Wire rope in elevators moving over pulleys and sheaves hundreds of thousands of times a year has produced inexhaustible data on wire rope flexibility. Building industry derricks with their heavier and varying loads have written another important chapter on flexibility. Still heavier loads are served by this derrick of derricks, lifting a fully loaded freight car smoothly and easily. Or contrast the specialized use in this coal loader. Next, wire rope must resist repeated stress in bending, in resilience and tension. Mine hoists carrying heavy loads of ore up and down day and night tell quickly how well the wire rope resists the strains of repeated bending. Likewise do skip hoists for steel blast furnaces. Then there's resilience and tension factors in repeated stress of oil well drilling. Yanking this rope millions of times before it's worn out. Wire rope must be able to resist shock or impact in serving the construction industries. Digging a rock out of the earth may put a stress on the wire rope many times greater than that of lifting it. Excavating the foundation of a building is like digging into an attic trunk. You never quite know what you'll find, but the wire rope on the shovel must be ready for any kind of a shock. And to a lesser degree, the wire rope on this road building machine must be able to take it. And abrasion. The wire rope that's pulling us up out of this mine has been scraping along the bottom all the way up. On the surface, this mine's incline railway gives its wire ropes more hard knocks as it drags its way up the side of a mountain, over pulley, through grit, across wood ties, and over steel switches. The wire rope must resist abrasion. In the thousands of miles of wire rope Roebling has made for the logging industry all over the world, Roebling engineers have garnered data to show them how to fabricate wire rope so that it resists crushing, as these logs smash the rope against rocks on the ground, against tree stumps, against other logs, again and again in tropic heat or frozen north. And finally, wire rope must resist corrosion, whether it be salt or fresh water, clean or sewage muck. When you've learned how to make wire rope that will take the kind and types of punishment you've seen, you're well along the way to making the wire rope that's safe enough for the Golden Gate Bridge. But you're not quite there until you've specially prepared each 3,600-foot length. Whatever non-elastic and unpredictable stretch exists in the rope must first be removed by a process known as pre-stressing. Another Roebling development for accuracy and safety. The rope is run out as a loop along an 1,800-foot track. By means of a large hydraulic testing machine, the rope is pulled or stressed far above any load it will ever receive in service, and held there long enough to remove all of the unpredictable stretch. Now the stretch can be accurately predicted, and the rope will be perfectly elastic. Then tension is reduced to the dead load tension to which it will be subjected on the Golden Gate Bridge. The lengths are now ready to be measured, marked, and then cut on a large shear. For socketing, the ends of the wire are spread out. Next, dipped in a bath of acid to remove the galvanizing and thus clean them. Then the socket is placed over the wires. The servicing or winding will be removed, and the wires again opened, spread out like the ends of a broom. Finally, molten zinc is poured in to complete the seal. At the Roebling Physical Testing Laboratory at Trenton, the final precaution is taken. Samples of the suspender rope are tested in a 2.5 million pound mechanical testing machine to make certain that these suspender ropes meet the highest specifications required. After the elastic behavior of the samples are studied, the load goes up and up. Up and up, and with the report of a cannon, the rope breaks. Then again, 2 parts of a rope this time. Up and up the tension goes. As rapidly as the suspenders are hung from the main cables, the main roadway is being hung onto these suspenders, always working out from the towers to balance the load. Large derricks called travelers attach the steel members of the roadway and its stiffening trusses to the suspender ends. Here the derrick is handling one of the diagonal members of the stiffening truss, which forms the side of the roadway structure and helps keep it rigid. Bridgemen in the connecting gang ride the steel and guide it into place. Only after all these steel members have been attached is it possible to make sure that everything is in its right position. Will the cables sag to just that point shown on the original drawings? Have the suspenders been pre-stressed to just the right length? Let's not worry about it. The bridgemen aren't. They're as confident that everything will set properly in place as they are of their own agility. Like the trapeze artists in the circus, these bridgemen get paid for it. But unlike the trapeze artists, the bridgemen don't charge the spectator and don't holler alley-oop. Now the heavy floor beam over which the roadway will run is swung into place and connected up. These beams are spaced 25 feet apart across the span. The beams are 90 feet long and 8.5 feet deep. When the traveler has placed truss and roadway steel as far as it can reach, it moves ahead and repeats the operation. In this manner, the Bethlehem Steel Company erected their steel for this roadway in record time. Almost 1.5 miles of it hung from the Roebling cables. The truss and roadway members, such as this floor beam, were received at the base of the tower on barges. From these, they were raised to the roadway level and moved out to the traveler on a temporary construction railroad. As quickly as the steel for the roadway is placed, wood forms for the 6-lane concrete roadway are installed. As steel sections which will strengthen the concrete are placed over the forms, then welded, a continuous supply of cement is moved out in train loads. Small hand dump cars are quickly filled and just as quickly dumped. Settling the concrete preliminary to the final leveling operation guarantees a firm roadway for the heavy traffic it will carry. This leveling machine makes a smooth, sure surface. A final wetting and the concrete roadway is complete. With the familiar white traffic markers. With most of the dead weight in place, it is time to start wrapping the cable. By means of this machine, a continuous winding of wire is placed around the cable between castings. This makes the cable completely waterproof. The wrapping wire is wound on 2 bobbins which envelop the cable. As the machine turns, a wire is drawn from each of these bobbins through a fair lead to its position on the cable. Small steel fingers crowd the wires into close contact with those already placed. Ahead of the machine, the bridgemen remove the flat wire bands. Wrapping wire is spliced by means of a butt weld. Thus, the cable is entirely sealed against the elements. The wrapping is broken only at the cable bands where it nests in under a 1-inch groove provided in the casting. This groove is then caulked to make the seal complete. After painting, the cable looks like a large iron pipe. The footbridge is no longer needed. Section by section, it is slid down toward the center. Here, each section is lowered and trucked away. While the completed cable is being cleared, the suspenders are painted. Each man lowers himself to his work point and paints himself down. He takes his lunch with him and stays on the job all day. What a picnic. As the spinning of the big cables proceeds rapidly, several other operations are necessary. Strands are wrapped at intervals to hold the 452 wires in place. Let's move up to a tower top with the help of this tow rope and see what else is happening up there. When a strand is completely wrapped, it must be lifted from its temporary position at the tower top to its final resting place in the large saddles. As the strand is hoisted by hydraulic jacks, its entire weight of 250,000 pounds is transferred to a lifting beam through Roebling flat wire bands and Roebling grommets. These bands are to remain in the cable saddle, so their thickness is restricted to 5/100ths of an inch. On this account, and because only a limited number of bands could be placed along the beam, and because the results of a failure of this wire would be so disastrous, one of the strongest flat wires of the many made by Roebling had to be selected for this purpose. Meanwhile, each strand is further adjusted at the anchorage. Here, the strand shoe is being jacked back to bring the strand to the correct tension. When in perfect adjustment, a solid steel pin is inserted to hold it fast. We all remember from our school books the physical law that heat makes steel expand and cold makes it contract. On a main cable 7,700 feet long, that may make the newly completed strand, just fully heated by the sun, several feet longer than the strands buried down in the interior of the partially completed cable away from the sun's rays. This physical law made strand adjustment uncertain until Roebling spread apart the vertical rows of strands in the cable to allow a circulation of air through the cable to help equalize temperatures. Never used on any bridge before, this new Roebling technique is an improvement in the interests of safety and accuracy. Until 27,572 wires have been spun to form each main cable, will the bridgemen hurry to the task. Finally, the last wire is to make the last trip. Befitting this great occasion, the carriage will be covered with flags. To some bridgeman, it is a lucky day, for the one who has guessed the closest to the time the carriage comes to the anchorage wins a pool. Let's listen in.
Here comes that wheel, fellas, and I'm gonna win that pool. You'll never make it in 20 seconds. Come on, boys. Come on. Oh, Ted got it. Ted's under the wire. It's Ted. Come on, pay off, men. Pay me.
And so on May 20th, 1936, 191 days after the first wires were strung, the spinning of the world's longest and greatest cables was finished in record time. Thanks to the planning and direction of these Roebling engineers and to the skill and loyalty of the bridgemen. After the last strand has been set in place and all erection equipment removed, we see the cable anchorage in its completed condition. This cross-section shows how firmly embedded in concrete and fully protected the cable ends are. Over the saddles, the completed cable will always retain the hexagon shape. In the spans, however, it must now be squeezed or compacted into a circular shape. After being compacted by this machine, the cable will be 36 inches in diameter, 3 inches smaller than the horizontal width of the hexagon made up of strands. If Bill would move over, we could see the compactor. The compacting machine consists of a heavy steel ring containing 12 radial hydraulic jacks, which squeeze the cable with a total force of 720 tons. One of the many Roebling flat wires is easily clamped around the cable to hold the cable wires in a circular shape or section after the compactor has moved on. Using a high-grade flat wire prevents the cable from springing back to its original shape after the tremendous pressure of the compacting jacks is released. With a template and scale, an engineer checks the final diameter of the cable. With the cable compacted, the next job is to place the cable bands on the cable. These are the castings which carry the hangers or suspenders. At the bottom end of these suspenders, the roadway of the bridge will hang. Cable band castings are made in two halves, which are clamped together tightly by means of bolts, and the friction thus developed prevents the bands from sliding downhill. The nuts are first taken up by a large wheel wrench turned by a drive rope around its rim. Which now carried 3 loops on each trip. Secondly, the wires were transferred at midspan. Thus, no spinning carriage had to travel more than halfway across, and the wire spinning capacity was doubled. These 2 Roebling developments have made it possible to open this bridge to the public in record time. At midspan, the wires were quickly transferred, and the carriages are now off on the return trip with a new set of wires. At the tower top, the bridgemen reach for the wire and place it loosely in specially designed clamps or vices. A little place the reel with a fresh one. The splice is identical with that made in the reeling plant. To control and guide the many spinning operations, a system of telephone and push-button lights connects many points along the line with the dispatcher's office in the middle of the bridge. Practically all sizes and types of electric cable required were selected from the large Roebling stock. Let's listen in as the main span dispatcher hears from the North Tower top spinning boss late one afternoon in May.
If South Anchorage promised you 2 more trips by quitting time, we'll top it, but clear 'em
over the tower top, they are placed in temporary saddles until a group of 452 wires form a single strand of the great cable. Let's go back to the building of the George Washington Bridge at New York and notice the great improvement 6 years has wrought in spinning technique. There, only 1 wire loop was carried on each trip. On the Golden Gate Bridge, this rate had been doubled. But Roebling engineers were not satisfied with twice the capacity. They wanted 6 times as much, and they achieved it on the Golden Gate Bridge with 2 developments never tried before in suspension bridge history. As soon as the bridgemen had become familiar with handling 2 loops of wire, the rate of spinning was then accelerated 50% by the introduction of a new type of spinning carriage. All the way down on the walk, a bridgeman attaches a hauling clamp or come-along to the wire. And 2,100 feet away at midspan, the wire adjuster operates the come-along by means of a push-button control. He raises each wire until it is clear of all obstruction, then lowers it to its position in the partially completed strand. When the adjuster is satisfied that the wire is in its proper place, he gives a signal to the tower top, and the bridgemen tighten the clamps on the wire. When the wire from one reel is exhausted, the spinning carriage must stop long enough to reach. Here is the strand shoe we saw in the animated drawing. Now, the spinning carriage comes into the anchorage. The wire loops it has carried all the way across from the opposite anchorage are taken off the wheels and looped around the strand shoe. Then, 2 more loops of wire are placed on the carriage. Off it goes for the return trip, moving up the side span to the tower top. As the wires pass over